All right, so I currently have that Excel assignment, which is due by the end of the day on Monday. I had quite a few people kind of reach out and get some help on that. If you're still kind of working through that and you have any questions, feel free to reach out. Monday, we've got office hours kind of between my classes, so 2:30 to 3:30 if you're needing some last minute help on that. I put up the next Connect assignment, which will kind of be some good practice going into that exam. So that'll be due kind of that following Monday, the 8th, and then we'll have the exam on the 10th. So that Monday, we'll probably do some review in class. We might even get a little bit of review next Friday. We'll kind of introduce the last topic today after we do a little bit of confidence interval stuff, kind of finish that up, and then we'll kind of finish hypothesis testing next week and lead us into some review for that exam. Okay. Any questions for me before we kind of get started here today? Okay. So we kind of rushed through some proportion examples on Monday, so I can show you how we do them in Excel. So I just want to kind of revisit those, show you guys some things we can do with confidence intervals in application, and then we'll kind of introduce or kind of start into that final topic before the next exam, which is hypothesis. Okay. So I've got an example here. It says iClicker. I'm not necessarily going to use it for iClickers today, but it'll be a good one. Anytime you see a slide that has the iClicker thing on it, it's always a good one to kind of go back, review, make sure you know how we solved it before you kind of take that exam. So here I had a survey, so we're going to get a little political in terms of being able to understand how we can apply these proportion examples to some politics examples, because those are some pretty relevant ones. So before the 2016 election, there was a survey. I believe this one was actually pulled from Fox News, trying to kind of find the most bias kind of towards the right that I could in terms of, can we predict the upcoming election? Right. So they had 912 registered voters, and 46% of the people in that survey said they were going to vote for Clinton. And I wanted to build a 90% confidence interval for the true proportion of people who are going to vote for Clinton. I can use what I know or we've already talked about to do that. So we looked at kind of that equation we had for our confidence interval for a sample, or for where the true proportion is. We'll build it around whatever proportion we see from our sample. So P hat kind of representing that sample proportion. We know that those sample proportions should follow a standard, or once we convert them into Z values, we follow a standard normal distribution. So we can figure out how many standard deviations away we need to go from that sample proportion to get our lower and upper bound. We then multiply that by the standard deviation of our sample proportions, which we had this equation for. So, this is where we could do the intermediate calculation and then just plug one value in, or we could kind of substitute that formula all into the same function or same formula, do it all at once. Either way, we should get the same answer. So here, in these problems, when we do confidence intervals, when it comes to the exam, we're going to have everything kind of given to us except for one thing. So we'll be told what the sample proportion is. Now we might have a little bit of work to do. For example, in this one, we're told 46% of people are going to vote for Clinton. So our sample proportion for people who were going to vote for Clinton in the 2016 election, right, would be 0.46. So we might be told the percentage, and we have to know, okay, proportion is just the basic decimal form of percentage. From there, the only other thing that we really need is our Z-score, because we plug in that 0.46 for our sample proportion. We have that sample size, 912. So the only thing we'll have to do is find that Z value, the number of standard deviations away we need to go. So here, if I want the 90% confidence interval, my alpha value is what? So what does alpha represent when we're looking at confidence intervals? The percent outside my interval in decimal form, right? Or said differently, the probability of being outside that interval. And so for the 90% confidence interval, alpha would then be 0.1, right? So 0.1 over 2, 0.05. So I'm going to look for that Z value that corresponds with seeing 0.05 in each tail, right? So really, I'm looking for that number of standard deviations away I need to go, right? The positive amount of standard deviations in the upper bound. subtracting that many standard deviations with a negative value would give me my lower bound. Okay? So I go to my table. Now, at this point, I could use the Z table, right? I can go look for what, 0.05. So looks like I'm in between these two values. So negative 1.64 and negative 1.65. I'm in between those two values. We said in practice, we kind of use the higher of the two. So 1.65 or negative 1.65. But we kind of ignore the negative sign because that's already built into our confidence interval formula. Now, another way we could do this, after last class, I said kind of a cheat, or not a cheat, but just like an easier kind of shortcut, would be I can use this very last row that has that infinite sign on my student T table. These would represent the standard normal value. So it's almost like, here's your comparison Z values in this last row. But if we only had if we had an example where we had to use the student T, here would be kind of the student T value. So that last row represented the standard normal. Right? So I go up here. I wanted 0.05, so I'm in this column, 0.05 in each tail, or alpha over 2, 1.645. So instead of only having to go to the second decimal, right, where we said we were in between 1.64 and 1.65, I could be a little bit more precise if I really wanted to use that value of 1.645. I think in the slides, I showed you what you would find if you just simply use that standard normal table. But in practice, if we use that last row, it would be a little more exact. Okay? Now, it shouldn't influence our answer too much. It might be off at like the third or fourth decimal if we had to round to 2 decimals there. But kind of either way, we should be able to identify what the correct answer is. Okay? So at this point, we really have everything we need to solve this problem, right? We've got a number for every single variable that we needed. It's a matter of doing this into a calculator. Okay? Now, in practice, one thing that might be easier to do this, if I had my calculator in front of me, 0.46 times 1 minus 0.46 divided by 912, hit enter, take the square root of that value. I would then have one value for this. I would then take whatever I get for that. I think it's see if I can remember correctly. 0.0146. 0.01645. So I have 0.0165. I would then multiply that by that 1.65 or 1.645 if I wanted to use kind of that last row of my student T table. I would have one value for what would we call this? The thing that we're adding and subtracting to our sample statistic we said is our margin of error. So I then have one value for that, and then that would make it a little bit easier. 0.46 plus whatever that margin of error is, 0.46 minus whatever that margin of error is. Excuse me, and that would give me my upper and lower bound. Okay. So I plug that in, right? I end up getting kind of my lower and upper bound of 0.43 to about 0.49. Any questions on kind of that procedure? You know, the examples where we had sample means were very similar. If I had the sample mean where I knew the population variance, I just had a slightly different equation here. We're calculating the standard deviation of instead my sample means. And if I only had a sample variance of the sample mean, the only thing that would really change then is I'm having to use that student T distribution as opposed to the standard norm. With this, yeah.
So that Z-score is always the alpha divided by 2.
Always.
You can just look it up, you're good to go.
Yeah, so we're basically going to keep finding the same values because our alphas are always going to be, of course, I mean, I shouldn't say always, but the majority of the time we're using our benchmarks of 99%, 95%, and 90% confidence. So we're going to start seeing the same Z values pop up over and over. Now for the T values, it's different because every single degrees of freedom, there's going to be slightly different T values, right? But yeah, for those Z values, we should start seeing the same ones pop up over and over. 1.65 shows up all the time. 2.58 shows up all the time, and 1.96. Right? Now we can do different levels of confidence. We could do 80%, but the kind of convention is we focus on those three kind of 90, 95, and 99% confidence levels. Any other questions here? So we built this confidence interval. I'm going to just plot it out. So we've got 20. So I'll try to keep it in line with 0.28, 0.4872. So what we're saying is the true proportion of people who are going to vote for Clinton, based off the sample that we found, is going to be somewhere in this range. We don't know where it's going to be. It could be here, could be here, could be here. But with 90% confidence, we can say it's somewhere in this range of values. Okay. From that same survey, we actually had the proportion of people who were planning to vote for Trump as well. So at the time it was 40% or 0.4. So I go through the exact same process. Everything's basically going to be the same. If I want to build a 90% confidence interval for the proportion of people who are going to vote for Trump, well, my alpha doesn't change. So I'm going to find the same exact z-score. Now, the standard deviation of my sample proportion will be a little bit different because I'm no longer looking at that 0.46. For Trump, this would be what? 40%, so 0.40. And then we'd be building that sample proportion around 0.40. But our sample size was, remember, from the same survey, right? So we just go through, right? We've got everything plugged in that equation. It's just a matter of getting that entered into our calculator. And we find the upper and lower bound of about 0.37 to about 0.43. So this kind of shows it kind of alludes to things we'll do actually after this next exam. You can actually be a little bit more precise and make the work a little bit easier. But now I can create a range of values for where that true proportion of people who are going to vote for Trump is. So if I plot that out, the upper bound is 0.4267. So it's close here, but not overlapping. This kind of corresponds to that last question on the Excel assignment. Once I have my confidence intervals, can I say anything about which one of these is going to be, can I say that one of them is going to be greater than the other? Well, if I look here, there's no overlap in my confidence intervals, right? So even worse, I shouldn't say worst case scenario, but worst case scenario, right? In terms of comparing these two, the proportion of people who are going to vote for Trump at most with 90% confidence would be this value. At least the proportion of people who are going to vote for Clinton with 90% confidence, I could say, would be this value here. Well, then this is higher than this. So with 90% confidence, I can say that the proportion of people who are going to vote for Clinton is actually greater than the proportion of people who are going to vote for Trump. So I can start to make predictions about elections, right, using this idea of confidence. And, I'm using the example of elections here, but this could be the proportion of, two different groups purchasing this specific product, or two different companies, portion of times they're going to, have positive returns, or whatever it is that I want to compare, right? But, I think everyone, this is somewhat recent, the election, or I don't know, we're always talking about elections. So you're always seeing these types of confidence intervals put out there in the media about the proportion of people who are going to vote for this candidate versus this other candidate. And this is really all they're doing, right? They're coming up with these confidence intervals. And I don't know, maybe there's political junkies in here, but anytime you hear them, they'll always say like, the current percent of people who are going to vote for Trump is, or whatever candidate is, 0.4 plus or minus, and then they give you a number. That plus or minus, what they're telling you is the margin of error, right? They're giving you basically the value you would need to construct your confidence interval. The reason they do that, well, I don't know exactly why. I would imagine the reason they do that is because if I'm just comparing the proportions here, very easily I can say that, well, Clinton, in the survey, it shows Clinton's going to get a higher portion of the vote, plus or minus some amount. Well, it's not as easy to envision if they give you that plus or minus, and that plus or minus was wide enough. So let's say instead of 90% confidence interval, I want to do the 99. What's the only thing that's going to happen? The only thing that's going to change? I still have the same sample proportions and sample size. My z value is going to change. If I want to say something with a higher level of confidence, what happens to alpha? So 90% confidence alpha is 0.1, 99. Yeah, alpha is going to get smaller. So what happens to the z value? I need to go a further number of standard deviations out. So my z value goes up, my confidence interval is going to get wider. I can almost guarantee that if you recreate this example with a 99% confidence interval, okay, it's going to push my lower and upper bounds out further. And now there's an overlap. So now maybe the true population portion for Trump voters is here and Clinton's down here. Or maybe it's here and here, right? So I can't really make any predictions at the 99% level. Because as soon as those confidence intervals overlap, all bets are off. I don't really know what the relationship is between these two proportions. So when they give you that plus minus, right, it's hard to envision whether or not those confidence intervals overlap for, just kind of immediately, right? That's why they try to just use the sample proportion that they see. Like I said, I'm putting my thoughts about what they're doing. I imagine that's why they do that. Any questions on this? Is making sense, or questions over any of the steps? Okay, so these next slides, we're not going to work through them. We're going to go through them pretty quickly. It's basically the same idea, but it's a little bit more recent. It's kind of interesting. This won't always be the case because I'm saying things with 90 and 90%, 99% confidence, right? So even though it's a high level of confidence, I'll still be wrong 1 or 10% of the time, right? However, if we looked at the 90% confidence in what we originally had here, I could have said that Clinton was going to get a higher proportion of the popular vote than Trump, which is actually what ended up happening in 2016, right? Electoral votes, that's a whole different story. We have to go like state by state, but at least for the popular vote, it's pretty easy to make predictions. So in 2020, we basically did a similar thing. So I think what I did here was there was some company that got it right in 2016 that like no one else was getting this prediction correct, right? That Trump was actually win. So I used their survey data from 2020 to think about, could we have predicted the 2020 election? Right? So here we had the true population proportion for Biden was what, 0.51 to 0.46, and then for Trump, 0.4 to 0.45. These confidence intervals even further from overlapping, right? We could actually probably have built the 99% confidence intervals here, and they wouldn't have overlapped as well, right? So in fact, in 2020, we probably could have predicted with 99% confidence that the portion of people who voted for Biden was greater than Trump, which would have once again been kind of proven to be true. Now, like I said, you can't do that every time. If I try to predict every single election, like for every candidate, even at the 90 and 99% level, even if the confidence intervals don't overlap, I still could be wrong, whatever alpha is percent of the time. So, but it's kind of a useful application of what we're doing. We actually see it being put to practice in the real world. So I wanted to kind of make sure we kind of show you these key examples. I then use like a different poll. I thought that was like going to be biased. Once again, I think I went to Fox News again, just to see if I took the most biased poll, could I end up with these confidence intervals overlapping? And whoops. And I think I had here for Biden 0.4888 was the lower bound, 0.49. So I did get the confidence intervals to just barely overlap when I took what I thought was probably the most biased poll. But we have kind of now know what the outcome was. It is kind of interesting. We can start to play around with these different polls. Always kind of being aware of the bias that might exist in each one. And if I was actually doing some practice, I'd probably try to find the least politically affiliated kind of organization that did these surveys. So we worked through examples last class for these sample means where we don't know the population variance. We then had to use a sample variance. Things look very similar, but we then started having to use that student t distribution. We saw how we do that with a couple examples. We also looked at it in Excel. I think, hopefully we spent quite a decent amount of time on these confidence intervals. That's going to be a good chunk of questions that you see on the exam. I would imagine you probably see one of each type at the very least. And kind of the idea behind them we'll have questions on, which is really all of this confidence intervals, the reasons why we know we can create this range and say it with different levels of confidence is because what we know about the distribution of sample means and sample proportions. So that's going to be a good chunk of what we kind of see in this upcoming exam. Any questions before I kind of introduce the next topic? Yeah.
Is the T-chart equation and the one who uses the T-chart who uses the table, is it the same equation just depending upon?
Yeah, so it'll be a little bit different, right? Kind of went over last class. There we go. Right? It's going to be a little bit different because we were looking at sample means. Whether or not we knew the population variance or not. So let's say we only had a sample variance. we're going to be multiplying by the standard deviation now of our sample means, not the standard deviation of our sample portions. Our sample portions, we know, have a standard deviation that will follow p times 1 minus p divided by n. And that's because we kind of took a look at that binomial equation and think about, well, that was the number of successes, we looked at the proportion. So it'll be a little bit different in that we're going to be taking the square root of now the variance of the statistic that we're interested in would just be us calculating the sample variance. Now, on the problems that you're going to be having in the exam, I'm giving you what that sample variance is. In practice, like when you do in Excel, you've got this variable. All you do is you could do by hand calculate the variance or var.s to give you that sample variance. Okay? So they'll look a little bit different, right? But it's the same idea, right? Because we're still, once we plug our values in, we're still getting our margin of error that we need to add to our sample statistic. It's just the sample statistic is slightly different. When the variable is a 0, 1 variable, and that's a proportion, right? We said if we take the average of 1, 0 variable, that gives us the sample proportion. It's just going to follow a slightly different form, right? But it's the same general principles and idea behind it. Is that?
Yeah, no, yeah.
And I did put up 2 practice exams. There's a folder in the files tab that says exam 2 practice materials or something similar to that. Has 2 practice exams, the answer keys. It also has the formula sheet that I will kind of include with the exam. So if you wanted to print that out and start kind of like the last one I said, a good practice would be write down next to every formula kind of what that represents. So on that formula sheet, you have 1 equation that represents the confidence interval for sample proportions, 1 for sample means where I know the population variance, and there will also be 1 for the sample mean when I only have a sample variance. Yeah.
When is the next test?
So that will be what, the 10th, or not next Wednesday, but the following Wednesday. So we'll kind of finish up hypothesis testing next week, do a little bit of exam review before we done. Other questions here? All right, so we went through this last class. The next thing that we're going to do is kind of extending off of this idea of the confidence interval. What we're trying to do is pinpoint down where the true value for the population mean or population proportion is. So we're going to take a slightly different approach and try to rule out certain values for that true population mean proportion, and we'll do that with hypothesis testing. Okay? So the idea of hypothesis testing is we want to know where the true population parameter is, whether or not that's a mean or whether or not that's a proportion. Today, I'll probably specifically be using that terminology of mean, but every time I say mean, you can imagine we do the same thing for the population proportion as well. So we're going to develop 2 hypotheses. We'll call this the null and the alternative. Okay? So this null alternative hypothesis are basically going to be complements of each other. So once I come up with what I want to test for, what I want to test for, what I'm trying to find, we'll say that's our alternative hypothesis. So maybe I'm doing something like, I think I have the example on the next slide, but maybe I'm doing something like, I want to test for whether or not the true mean of a specific variable, I believe, if I remember correctly, is less than 7. Right? Or in the example I'll use, less than 7%. We're thinking about, I think, ABVs or alcohol by volume. So whatever my alternative hypothesis is, that's what I think is true. That's what I'm trying to find. Well, whatever I'm trying to find, I'm going to stack the deck against myself with the null hypothesis and assume that the opposite is true. Right? So the idea here is like, does the average beer kind of have an ABV less than 7%? Maybe that's what I think is true. So I stack the deck against myself and assume the opposite is true. My null hypothesis is what I'm assuming to be true. Okay? So I then go out and I take a sample, right? And I see, well, so if I think about, if I just have 1 sample, I'm going to use this assumed true mean, which we'll kind of call mu subscript 0. It's the value that we're assuming the population mean is. If 7 was in fact the true population mean, my sample means should be normally distributed around that, as long as I get a sample size over 30. Right? So then maybe I take a sample and I see a sample mean somewhere down here. This is evidence, right, that goes against my null. If I've assumed that that population mean is greater than or equal to 7, and then I see a sample mean of 4.9 or something, well, that goes against what I assume to be true, right? So if I can find evidence that goes against that null enough, then I'll end up rejecting. Now, you can imagine, even if I found evidence that goes against that null, maybe I see a sample mean of 6.8. Well, seeing a sample mean of 6.8, yes, that does go against my null, but even if my null was true and that the true population mean was like 7 or 7.1, it would be pretty likely for me to see a sample mean that was 6.8 or something close to that. Now, if I see something like 4.5, that's quite a bit different than what I assume to be true. That's probably strong enough evidence where I can say, yeah, what I assume to be true probably isn't in fact, isn't the real kind of value for that population. So that's the idea behind kind of what we're doing. I'll kind of explain more in more detail, but I just wanted to kind of present like a roadmap for where we're going. Okay? So if we don't have sufficient enough evidence, like these values of 6.8, then I probably don't reject my null, right? So we're going through, we're taking our sample evidence and determining whether or not we can reject our null hypothesis. So I think this is the motivating example I had. Really, everything I've said is kind of in this slide, right? I'm assuming I wanted to test to see, is the average ABV less than 7? So I assume the opposite is true. That becomes my null, right? That it's greater than or equal to 7. So notice that alternative and null hypothesis are basically complements of each other. I go out, take a sample. From that sample, I try to determine, based off of my sample mean, can I reject this? Right? I will walk through why seeing a sample mean, like where's the threshold, right? At 6.8, I probably shouldn't be rejecting the value of 7. 4.5 seems like I probably should, but how do I like set the threshold for like what's far enough away from that assumption to where I can actually reject it? Like, that's what we'll end up kind of doing. So a little bit more about the null and alternative hypothesis. Here's kind of our more textbook definitions, but I've kind of already said the alternative is what we're trying to find. The null will be kind of the assumed true state of nature, or what we're trying to find evidence to go against that. If we can find enough evidence to go against that, we can reject the null, or against that assumption, we can reject it. So we'll write this H subscript 0 and H subscript A. So sometimes in the book, or that next assignment, I think some of the last couple of questions on there are some practice, I'm putting them on there so you can do some practice before the exam, like working through these hypothesis testing examples. Sometimes they'll put H subscript A as H subscript 1. Right? I think it's way easier to put H subscript A, so on the exam, and anything I show you, I'll typically kind of always use that H subscript A to identify the alternative. If you look at like a statistics textbook, typically sometimes they'll put H subscript 1. And that's kind of the convention they use in mathematics, but I'm a little bit more focused on application. So we've got these two hypotheses. We then kind of can think about what are different types of hypotheses that we could have. Right? So if we conduct this test, right, potentially we have 3 different outcomes. Right? So either we find sample evidence that's very inconsistent with the null hypothesis, and we reject the null. That would be kind of like my 4.5 sample mean over here. The other 2 scenarios are we see something that's not inconsistent with the null. So if I see something that's not inconsistent with the null, in our example, that would be something like seeing 8%, right? That actually is a value that would support that null hypothesis, right? Because if we assume it's greater than or equal to 7 and we see a sample mean that's 8, well, that supports the null. Why would I ever reject the null in a situation like that? And then our third scenario is we find evidence that goes against our null, but not very much, right? And from what we know about the distribution of sample means, because that isn't very far from our assumed true mean, even though it's evidence that goes against the null, we still would fail to reject it, right? Because we know it's relatively pretty high probability that we saw that value. Okay? All right. Any questions? Kind of just over the general setup at this point. Obviously, we shouldn't be like completely comfortable with it yet, but any like glaring kind of questions or thoughts here. Okay, so I always like to kind of at this point walk through an analogy where we can start to think about the null and alternative hypothesis in less of like a numbers situation. Okay. So let's think about a court case, right? If we're thinking about let's like go real dark. We'll say it's like a murder trial, right? So I'm thinking about the null alternative hypothesis when someone is at a court case for a murder, right? Well, what are we trying to test for in that situation? Or what would our alternative hypothesis be? Yeah, I'm trying to, like, I brought them in because I think they're guilty. That's what I believe is probably the case. That's what I want to test for. That's my alternative hypothesis. So what do I do? What would my null hypothesis be? I stack the deck against myself, and I assume what? Well, hopefully, I assume they are innocent until proven guilty, right? So my null alternative hypothesis, right, would be that I assume the person's innocent, even though really what I'm trying to test for is whether or not they're in fact guilty. So this is kind of lined up with what we're doing here. We think that the average ABV is less than 7%, so we assume the opposite is true. And just like a court case, now, in order to see if I can find evidence that goes against my null hypothesis, well, what we do in a court case, we go out and try to collect evidence, right? Where's their DNA at the scene of the crime? Did the person have, an alibi? Do they have motive, right? And if we can find enough evidence, right, that goes against that null, we would reject it. Which in the court case example means if I can find that there's DNA evidence at the scene of the crime, maybe they found the murder weapon at your home, you didn't have an alibi, you reject the null and that person goes to jail, right? You reject the fact that they're innocent because you've had enough evidence to support the opposite of the null or support the alternative, right? That they were in fact guilty. If you can't find enough evidence, right? So maybe, no DNA evidence of the crime, they have a murder weapon that's similar to what they think was used. They don't really have a solid alibi, if there's no real motive, right? You found some evidence that it could be that, but not strong enough. Well, then you fail to reject the null that the fact the person was innocent, and so they go free. Right? And I think I have an OJ part here, so the glove doesn't fit, you must have quit, right? So I think being able to picture this in the context of a court case, it really kind of lines up with helping us think about what we're doing with numbers, right? And sometimes it's easier to think about non-numerical examples. Okay? Any questions? Yeah.
So the alternative hypothesis is just the opposite of the hypothesis of the time.
Yep, they're just going to be complements. So notice here, if I want to see it's less than 7, the complement of that's greater than or equal to. Other questions? All right, so we have some different types of tests that we can run, right? So I gave you an example where we were kind of wanting to, we assumed that true mean was greater than or equal to a specific value, right? We can imagine that's not always going to be the case. Sometimes instead of wanting to test for whether or not it's less than a certain value, we might want to test for whether or not it's greater than a certain value. Okay? So we're going to start out thinking about there are potentially 2 different types of tests that we'll call one-tailed tests. So the way that we'll write this is that our null hypothesis is going to be that the true population mean is less than or equal to whatever that assumed true value is. So mu subscript 0 in practice, that'll always be a specific value, right? That'll be the value that we think that the population mean is less than or equal to or greater than. So we'll call these 2 different types of tests, greater than or less than, which is basically, you can always think about the name of the test is based off of that sign in your alternative hypothesis. So think about it this way. If I've got that greater than test, really what I'm thinking about there is, and I'll use just kind of a general formula. So for the greater than test, I've assumed the true population mean is less than or equal to this value. So the only sample evidence that would go against the null is if I see something on the right side of the distribution, right? If I see something that's greater than that assumed true value or something that supports the alternative hypothesis. So this greater than test, when I have a greater than sign in my alternative hypothesis, I'll sometimes call this a right tail test. For a left tail test, a less than test, I've assumed that true mean is above a certain value, right? So now I'm assuming that the true population mean is somewhere in this range. So the only sample evidence that goes against that null is if I see something on the left side. So we would sometimes call the greater than test a right tail test and a less than test a left tail test. We then also have the hypothesis, maybe I don't care what direction it's on. So maybe I'm testing for like, well, where's the true population mean income value, right? And I don't know if it's above or below. So I just want to know, is it something different than 50,000, right? Maybe I've seen some old data in the past and I think it's 50,000. Well, then I could see a sample mean. And if I see a sample mean of 45,000, or I see a sample mean of 55,000, both of those would go against my null hypothesis in that case, right? Evidence on either side of the distribution could go against the null. So if this is ever the test that we have, we'll call this kind of our two-tailed or our two-sided test. And once we get to kind of calculating something that we'll call p-values, this changes a little bit. It's a little bit more, I don't want to say complicated, but there's another additional step if we have a two-tailed test. So these are essentially the three different types of hypothesis tests that we'll have: less than, greater than, not equal to tests, or right-tailed, left-tailed, two-tailed tests. Okay. So some of the things that we need to make sure, these really aren't that tough, but we need to determine what statistic we're looking at. Are we thinking about a population mean or a population proportion? That's not a very difficult step most of the time. From there, we need to determine what type of test we have. Is it a left, right, or two-tailed, or one or two-sided? And then we always include the equality in at least one of the alternative of the null. So it can't be in both. So notice the equality here, kind of by convention, we always keep that in the null hypothesis. At some point next week, I'll show you why that really doesn't matter. If you put it in the alternative or you put it in the null, but it has to be in one and only one, right? These are complements, so I can't put it in both. Otherwise, well, now there's a value that would be in both of these, right? Complements should be mutually exclusive. So just by convention, though, we always kind of throw that equality sign in that null hypothesis. Okay. So let's go back to our example here. What would our null and alternative hypothesis be if I'm wanting to test for whether or not the average ABV is less than 7%? Well, that's what I'm wanting to try to test for, what I'm trying to find. So what I'm trying to test for, what I'm trying to find, that would be my alternative hypothesis. So we can write this out in English, right? And what I'm trying to test for is whether or not it has an ABV lower than this 200 or lower than 7%. Right? I chose a very specific here. I like it. So is it less than 7%? I then assume the opposite is true, which is that it's not lower than that 7%. Right? Writing this out numerically, right? My alternative is that it's less than 7, which means I assume the opposite is true. I stack it up against myself, which is that mean, true population mean, is greater than or equal to 7%. So based off of the last slide, what type of tailed test do I have here? So the type of test we have kind of identifies what side of the distribution would provide sample evidence that goes against my null. So in this case, the only sample mean values that would go against my null would be values on what side? What's 7? The left, right? So it's a left-tailed test, right? Or a less than test. The type of test we can identify based off the alternative hypothesis. Right? Because the only evidence that goes against the null would be evidence that supports the alternative. So if I had a different type of example, what type of evidence in this one would go against the null? So I'm going to open this kind of icon. I'll keep talking to kind of maybe help you identify this one. Well, let's say that the economist wants to test for whether or not the mean retirement age is something different than 67. So if you're trying to identify the null alternative hypothesis here, and you want to test for whether or not that true population mean retirement age is something other than or different than the value of 67. Which of the following would be your null alternative hypothesis? So think about values that would go against your null or values that would support the alternative here. So what you're trying to find or what you're trying to test for, that's your alternative hypothesis. What you're trying to find or test for here is the true population mean any other value that is not 67. Give you a little bit of time to think about this, and then we'll kind of go over it. All right. If you haven't gotten an answer in, take your best guess here. 25 of us, everybody got an answer in? All right, I'm gonna close it out. So if I'm wanting to see, is it any other value other than or different than 67, what's my alternative hypothesis? So I would see if something is different than 67, I would say that it is not equal to 67. So what I'm wanting to try to find, that's my alternative. So if I want to see is it not equal to 67, that's my alternative hypothesis. I then assume the opposite is true, which is that is in fact equal to 67. So anytime that I have this term different than, right, or different from some specific value, those should actually be a little bit easier to identify. That's a two-tailed test. And the only way we have a two-tailed test is if there's a not equal to sign in the alternative and an equal sign in the null. Okay? So here we've got a situation where if I saw a sample mean of 70 or I saw a sample mean of 62, both of those would go against the null, right? And support the alternative. Because the null here is kind of easy. It's like one specific value. Right? If I see anything other than 67, that's evidence that goes against the null, that null hypothesis. Okay? Any questions on how you identified this? Okay. So here, I'll try to provide you evidence, just records my voice a little better. I'll give you a roadmap of what we're going to talk more about next class. So it's going to take a little bit of time. So we've got this sample mean distribution. And if we go back to that example, we're thinking about the population mean. And we assumed it was greater than or equal to 7%. Okay? So think about it this way. The only sample evidence that would go against this null and support the alternative is something below 7. So if I see sample evidence that's far enough below 7 that I could reject the value of 7 as my true population mean, well, then I can reject any other value above 7 as well. So whenever we have kind of this greater than or equal to, we use that cutoff value. Because if we can reject 7, well, then we can reject 7.1. Think about it this way. If I see a sample mean of 4.5, well, if that is sufficient enough evidence to reject the value of 7, then I could also reject the value of 8. I could reject the value of 8.5, right? Any other value higher than. This sample mean just starts to become more and more inconsistent without those values. So all I'll do is kind of choose that lowest value in that range. And if I can reject that value, I can reject every other value as well. So how do I determine if 4.5 is different enough from this assumed true mean of 7 to be able to reject it, right, as the true population value? Well, we know certain things about the distribution of sample means. So what we know is that they should be normally distributed. So I should be able to turn this value of 4.5 into a z value. So if we think about how we typically do this, we would take that sample mean value that we found, or 4.5, we would subtract the true population mean, and we would divide by the standard deviation of our sample means. So the equation we had for that was just the square root of whatever that known population variance is over my sample size. So we're going to start out, kind of like with confidence intervals once again, start out with examples where we assume that someone has given us that true population variance. Not the most practical, but we need to walk before we can run. So we'll work through these, and then we'll see how we do this when we have only a sample. So the only problem here is I can't see what that true population mean is, but I do have this assumed true value. So I'll use that assumed true population mean. I can find how many standard deviations away was my sample from that assumed true population mean value. Once I have the z value, I can look it up in the table. and I can come up with the probability that if this was in fact the true population mean, the probability I saw the sample mean that I did or anything even further from that assumed true value, that probability is represented as the area in that lower left hand. Right? So what we're going to call this is our p-value. So this p-value is going to represent the probability I saw the sample mean value that I did that was as far away from that assumed true mean, if in fact this was the true value, or anything even further away. So I think I'm going to skip through these and I'll go a little bit out of order here. Just show you one more thing before we leave. Oh, I guess I didn't include it. So I have it in next week's slides. So we don't have to worry about this. So once I have that p-value, you can think about it, I'm going to start to set thresholds. So if this was in fact the true mean, the probability that I see 4.5, if that probability falls below this threshold, then I'm okay rejecting this as the assumed true value. Because if the probability, let's say, of seeing 4.5, if in fact the true mean was 7, let's say I look this up in the table and I find that this is, I don't know, 0.0032, right? Has a really low probability of occurring. Well, if it has a very low probability of occurring, what's probably more likely to be true is that the true distribution of my sample means probably has a much lower, like the population mean value is actually much lower. Right? Because if this was the true population mean, then it would be very likely for me to see the sample mean that I did. So if we start to see these probabilities, these p-values get really small, it's probably that what we assume to be true isn't in fact true, and this green distribution will be the more likely scenario. So what we'll do is we'll start to set thresholds for alpha and say, if the probability or if the p-value here falls below 5%, right, or falls below 0.05% in decimal form, then I'm okay rejecting my null hypothesis. So we're going to turn our sample means into these z values, which next week the next class we'll start to call them z statistics, kind of identifying that they're a z value, but before a hypothesis test. From that z statistic or z value, we can find our probability of seeing something that far away from the assumed true mean or even further, or what we'll then start calling our p-value. If that p-value falls below this threshold we set, then we're okay rejecting that null hypothesis. If it doesn't, right, like maybe I see a sample mean of 6.8, I turn that into a z-score, that p-value is like 0.4, well, that's not very low, right? That's probably not going to be below these threshold alphas that I set, which will correspond to really the same type of alphas that we were using with confidence intervals, 0.01, 0.05, and 0.1, right? If the probability of what we saw falls below 10, 5, or 1%, we're okay rejecting the null. So we'll talk more about that next week on Monday. We'll start working through some examples. Basically Monday, Wednesday, a little on Friday, we'll have the same 3 types of examples that we did for confidence intervals, okay? All right. Have a good weekend, and I will see you guys on Monday.